technology. So, you know, like it's a pleasure to introduce you because like I've always thought of this HQ meeting as a meeting of like historians, philosophers, and physicists. He's going to be talking to us with a very Sherlock Holmesian title, The Curious Case of the Disappearing Wave Function.
Thank you. How do I turn this guy on? Working now? That's good. Let's see. I can do this. Okay, and whoops, that's not going to work. Oh, now I'm completely tied up with my glasses. Huh? That's a disaster. How do I get this thing going? It's in Spanish. Terrific. Which of these do you know how to operate this? It's all right, Jaume, I don't know what I'm doing. Okay, thank you. And let's see if this is going to work. Okay. Well, I certainly want to thank the organizers, and Jaume has done a wonderful job. And I actually want to thank all of you, because I've only been working in this field for a year and a half, and all of you have been very warm and welcoming. And it's quite different than when I changed fields inside of physics and nobody would listen to anything I had to say. You've been very kind in that regard, or perhaps we'll find out in 30 minutes how kind you are. In any event, so the theme of my talk is the curious case of the disappearing wave function. So there it is, the lonely wave function. And here's a fact which may or may not be well known to you, and that is that the many electron wave function that we've been hearing about for the last two talks plays virtually no role whatsoever in the vast majority of contemporary calculations of the properties of atoms, molecules, and solids. And I'm talking about actual atoms, you know, like krypton, an actual molecule like lithium hydride, an actual solid like tantalum disulfide. So people who want to know the properties of a very specific system do not solve the Schrodinger equation. They do not calculate a many-body wave function to calculate properties. So you cry, how can this be true? And so I'll try to explain that. And then in particular, how did this happen? So that is going to require a discussion of what I'm calling here the natural history of the many electron wave function, psi. And I divided it into these time blocks. So there's the heroic period, the foundations period, from 26 to 30, where psi is calculated for 2 electron systems, the original many electron problem. Then there's a period which we might call the Dark Ages, from 1930 to 1950, where psi is calculable for atoms, but essentially impossible for molecules and solids. And so there's a period of methods development, but no actual numbers can be calculated. There's a breakthrough in 1950, and this breakthrough is associated with the advent of modern digital computing. From 1950 to 65, where the many electron wave function for molecules and sort of for solids begins to appear. And then the crucial year is 1965, as we'll see, when the many electron wave function disappears for solids, and that persists to this day. And the chemists, the quantum chemists who are responsible for molecules, are a little slow to get on to the bandwagon of killing the wave function, but they finally do in 1990, and that persists to the present day. So what can all this possibly mean? Let's begin with the first many electron wave function which is ever discussed. This is in the 4th part of Schrodinger's famous quartet of papers on the quantization as a problem of proper values. He talks, he doesn't write anything down. It's all in words. Most of the papers, as you well know, deal with the 1 electron problem. But he talks about an n-electron, n-particle wave function. He says that it lives in a configuration space where, let's see, is this the pointer? Well, I don't see it. Where it lives in a space where R1 is short for x1, y1, z1, the Cartesian coordinates of particle 1, r2, et cetera, for particle 2. So there's a 3n dimensional space for this quantity. He then, interestingly, talks about how you would calculate the electric charge density associated with this wave function. And he, again, in words, describes exactly this little formula I've written down. Now, he then gets into a big mess interpreting the wave function, and Heisenberg attacks him and everyone else, and Born eventually promulgates the statistical interpretation. But as it happens, this formula that Schrodinger talks about is exactly correct. And if you have a many electron wave function psi, that is in fact how you calculate the electric charge density associated with a collection of electrons, and I'll be talking only about electrons. And this density will be important as we move forward. So Heisenberg and Dirac in the same year show that a determinant constructed from one electron orbitals, so phi sub a of r, an orbital which holds one electron, that if you construct this determinant, then the many electron wave function has the proper anti-symmetry to build in the Pauli exclusion principle. And so I will use this notation DET with the brackets there to indicate this giant beast of a wave function. And so that's what you're supposed to do. And it is Heisenberg who does the first legitimate many electron calculation. This is done for, in order to understand the singlet triplet splitting of the excited state spectrum of the helium atom. Clayton showed us the spectrum at the very first talk of the meeting. He wasn't able to discuss the ground state because spin wasn't really understood, but the excited state splitting he did understand, and in particular, that you're supposed to multiply these one electron wave functions together. So the A and B here indicate orbital labels, for example, 1s and 2s, and R1, R2 are electron labels. And these two combinations, the symmetric and antisymmetric, correspond to the singlet and triplet solutions. And we now know, of course, you have to multiply by a spin function to get overall antisymmetry, but that wasn't germane to what he was doing. But nevertheless, this, and of course, it's Heisenberg who understands the exchange energy and how that's what produces this splitting. Now, almost immediately thereafter, Heitler and London use Heisenberg's method. They actually use his method and his algebra. They simply steal it completely. And instead of talking about two electrons, on one nucleus, you're talking about two electrons on two nuclei. They used it to study the binding energy of the hydrogen 2 molecule as a function of the HH separation. They produced this famous graph where, again, the symmetric and antisymmetric solutions are what are relevant. And in this case, it's the symmetric space function, which has a minimum in the binding energy, and it's the antisymmetric space solution, which is purely repulsive. And this can be regarded, if you like, as the beginning of quantum chemistry, which takes off on a direction which I'm going to describe, because those are the folks who've taken the many electron wave function to its greatest heights. So, what does that mean? Again, 1927, Friedrich Hund and Robert Mulliken introduced the idea of a molecular orbital. And so this is the generalization of what Heitler and London had done. We now have, again, a separation of variables here. R1 corresponds, say, let's do a diatomic molecule, or H2 again, for example. The same meaning. R1 is one electron, R2 is the other. And they're going to choose, in this particular simple case, the same molecular orbital for both. But each orbital is written as a linear combination of atomic orbitals. So phi A and phi B are atomic orbitals, and the C1 and C2 are arbitrary coefficients, which need to be determined. So we're adding, if you like, variational freedom to the molecular orbital for particle 1, and we do the same thing for particle 2, and therefore we have a product of exactly the same functions. Now, what do you have to do to implement this? You have to choose the atomic orbitals, and at that time all they had were the hydrogen solutions. So that's what was used. You then determine those variational parameters, the expansion coefficients, and you do that simply by inserting this guess wave function into the Schrodinger equation, all right, the normal Schrodinger equation, and that determines the coefficients, where, just for preciseness, the Hamiltonian consists of the kinetic energy of the electrons, the potential energy between the fixed ion and the electron-electron interaction, which is the hard part. And this starts a long Mulliken down a very long road of calculations where actually most of the these orbitals and the various things which enter into calculating that matrix element are done empirically or by guessing, but not really by doing much in the way of calculation. Now, Slater, then, in a famous paper, generalizes this idea even more and says, well, we'll write the many electron wave function now not as a single determinant as had been done previously, but as a linear combination of determinants. And so now we have a hierarchy of more variational parameters. So each molecular orbital, called chi here, is a linear combination of atomic orbitals. So every time the word linear combination appears, we have extra unknown parameters to determine. And then we've already seen previously that the determinant is a combination of those things. Here we have the CKs, yet more parameters, but the idea is the same. You determine all these unknown coefficients, if you like, by minimizing the energy of the system or solving the secular equation. It's all turned into a matrix problem ultimately. The key idea already understood by Slater is that if you increase the number of determinants in the wave function, you increase the variational freedom, then you're going to get a better and better solution, a lower and lower energy. And so it's just a question of more and more of these undetermined coefficients. So this is called the method of configuration interaction, CI, which was called charge independence earlier today. It's going to be configuration interaction in this talk. And so this now becomes a well-established method in quantum chemistry. The trouble is that when you take these multi-determinantal wave functions and you evaluate matrix elements like indicated there, you get what was called a nightmare of integrals. A typical integral you would get is shown here. It's a double integral of the Coulomb operator, 1 over r minus r prime, and 4 orbitals. And those orbitals have A, B, C, D. They have different indices, so they could be S functions or P functions, D functions, and they could be located on different atoms. So I show a methane molecule on the left where I've put 3 S functions on 3 hydrogen atoms and a P function on the carbon. And you then have to evaluate that integral. And don't forget, it's difficult to even know what the orbitals should be. All right? And so in fact, Slater, once again, who's a hero in much of this, suggests simple analytic forms for that, which are called Slater orbitals, shown there at the bottom, which have an undetermined parameter gamma. And even using these analytic functions, these integrals are ferociously difficult to do. And so it makes it extremely difficult to make progress from first principles. Again, people often approximated the matrix elements empirically in order to make progress. John Popel, who received the Nobel Prize in Chemistry for quantum chemistry basically in '98, pointed out that a big development was made in 1950 by Samuel or Frank Boys, who took the Slater type orbitals and expanded them in a linear combination of Gaussian functions, e to the minus kappa r squared, with some other simple algebraic functions in front. Now, by writing a Slater orbital in this form, you again massively increase the number of integrals you have to do, but because it's Gaussians, you can do them all analytically, every one of them. And so it becomes a titanic storage problem on the computer, but not one of doing difficult integrals anymore. And this is what actually makes quantum chemistry go after 1950. And it's a question of bigger computers, faster computers, more storage, in order to diagonalize the Hamiltonian and get the spectrum and everything else. So the high point of many electron wave function here is that psi is a linear combination of configurations. Each configuration is a linear combination of molecular orbitals. Each molecular orbital is a linear combination of atomic orbitals. Each atomic orbital is a linear combination of Gaussian functions, and there's all these parameters everywhere, all of which you determine by doing the appropriate minimization. The first such calculation was done by Douglas Hartree, his father, and Bertha Swirls, who later becomes Bertha Jeffries, in 1939, where they used 2 configurations, 2 determinants, to study oxygen plus. And I just took a recent example from the literature just to show you what happens in quantum chemistry these days. That is 2.8 billion determinants which are added together, and that's just for the chromium dimer. Suppose you wanted to know a protein. It's hopeless. So quantum chemistry cannot do such problems. This configuration interaction method doesn't work for solids at all for various technical reasons. Early practitioners hoped they could get away with a 1 determinant solution, And that suggests Hartree-Fock. And Jean-Philippe told us about Hartree-Fock. Here I've actually written down the Hartree-Fock equation. And as he pointed out, there's a part of it, there's the kinetic energy, which we understand. There's a periodic potential from the ions. There's an electrostatic potential that comes from the charge density of the electrons. This is a mean field. The charge density on the right there is simply a sum of the one electron orbitals. But there's this unpleasant exchange potential at the bottom, which is non-local, which means that the orbital I'm trying to calculate in this Schrodinger-like equation, psi k, is inside the integral. And you have to do the integral before you can solve. So it's an integral differential equation, which is a numerical disaster. Moreover, everything is supposed to be solved self-consistently. Once you solve this once, you calculate rho, you have to put it back into the Coulomb potential, and you go around to self-consistency. It's a terrible numerical problem, and so people didn't do it. So this is where Slater's breakthrough that we heard about earlier is relevant. He says we'll replace this non-local operator by a local potential. A local potential. It's called V Slater here. And this is the paper where he also explains the physics of the exchange whole in a very beautiful way. And this is just a Schrodinger-like equation. And so it's easy to solve, and band structure calculations start to appear at an enormously rapid rate at this time, because this is a numerical problem one can solve. Now, this persists until 1964 or 5. And here's the man who makes the many electron wave function disappear. His name is Walter Kohn. This is a photograph from about 1963. Walter is he's still with us, a card-carrying theoretical solid-state physicist who shared the Nobel Prize with John Pople, who I mentioned earlier, in 1998 for chemistry, not for physics. Now you'll see why. What he did was invent something called density functional theory. This is an approach to the many-body problem, to the electronic structure of matter, where the n-electron wave function is eliminated entirely as the fundamental quantity, and it is replaced by the electron density. Now this is an astonishing thing, because psi is a function of 3 times capital N variables, where n's the number of particles, and the electron density is a function of x, y, and z. So you've replaced a configuration space of size 3 times 10 to the 23rd with real space, if this could possibly be true. Now, this is the problem that Kohn was thinking about when he discovered this result. It's a very mundane problem in a way. It's how do you calculate the electronic properties of an alloy? An alloy is, you have a periodic lattice, but the identity of the atoms at the different lattice sites is random. So if your 2 atoms that you're throwing randomly at a lattice are zinc and copper, you get brass, for example. And he wanted to know, how do you solve the Schrodinger equation? Because without a periodic potential, the potential is no longer periodic, all of the methods that had been developed in what I call the Dark Ages were not useful, and Kohn himself had developed several of them. So this is an outstanding problem, which still there's nothing close to an exact solution. But he was worrying about this, and so in his Nobel lecture he says, in the metallurgical literature, because an alloy, that's metallurgists, that's what they do. I found the concept of an effective charge for each atom in an alloy. The electrostatic interaction energies of these charges are part and part of the total energy, which is true, it's a Coulomb thing. Thus, there was a natural emphasis in the literature on the spatially varying electron density, rho. The question occurred to me whether knowledge of rho alone determined the potential energy, V ion. If you know V ion, and in principle, put that in the Schrodinger equation and you get everything else. So this is truly a eureka moment, as far as I can tell. The only problem is, I spent about 6 months living in the metallurgical literature. I can't find anything like what he says here. And when I asked him, he can't remember what the papers were. So it's even more remarkable that he came to this guess that it could be true. The Schrodinger equation is a functional, from the Schrodinger perspective, every observable is a functional of psi, by which I mean you give me psi and I calculate a property. The Hollenberg-Kohn theorem, and Pierre Hollenberg was a postdoc in 1964 with Kohn, you show that every observable is a functional of rho. In other words, you hand me rho, and then in principle, I can calculate every single property, the spectra and all of the observables. It's quite a remarkable theorem. It takes exactly 2 lines to prove, but it hadn't occurred to anybody to even consider this possibility, even though people like Thomas and Fermi had their approximate theory long ago. They never suggested that it could ever possibly be exact. It was always an approximation. This is an exact result. Hans Primus was a theoretical chemist and philosopher who actually realized very early on that this had great significance, feasibility for a complete renormalization of quantum chemistry. But it wasn't really believed by chemists for some time. The theorem remains a bit true but vacuous for 1 year when another postdoc, Lou Sham, joins Kohn, and they derive a set of one-particle equations which look very much like the Slater equations. In fact, everything is exactly the same as the Slater equations, except that thing called VXC takes the place of what I had previously called V Slater. It's a local potential. It's unknown, but if you do know it, then this solves the exact many-body problem, the solution of these equations, which is easy numerically because it involves a local potential. So if this were known exactly, one could calculate rho and the total energy exactly. And so the game is to make as good an approximation for VXC as you possibly can, because if you have the great good luck to hit the jackpot and get the right one, you're done. You've solved the many-body problem exactly. So, of course, it's not known. Kohn and Sham suggested an approximation known as the local density approximation, and I've written it down right here. Interestingly, one piece of it is closely related to Slater's suggestion, but there's another piece which they took from some much earlier work by Wigner, which has to do with the short-range repulsion between anti-parallel spins. Of course, the exchange interaction involves parallel spins, keeps them apart. You need something to keep apart the anti-parallel spins, and that's this extra piece. People started using this. Excellent results were obtained for the properties of solids. Now, you might say, why do I say there's no wave function? That looks like the Slater equation. There are these orbitals. Let me just take the orbitals and put them into a determinant, and isn't that the wave function? But it's not true. The orbitals in density functional theory and the eigenvalues belong to a fictitious system which happens to have exactly the same charge density as the real system. This is the trick that's involved in their work. So if I go back to Schrodinger and his formula for rho, then if I have a fictitious system and a real system which have the same density, that does not imply that they have the same wave function, obviously. All right? And so it is not the case that solving these what are called the Kohn-Sham equations give me the many-body wave function. They don't. They give you the correct density, but that's all. Now, people have been using this for quite some time. Because it's so numerically easy, people abandoned Hartree-Fock, they abandoned CI, chemists, and started using this. And the temptation to use the fictitious wave function and to pretend that it is the real wave function is overpowering. And so people use it anyway. And so even though the exact many-body wave function is dead, it actually appears and lives on as a zombie. This fictitious wave function is used by many people as if it were the real one, but it is not. So here's sort of a DFT timeline to give you an indication of what happened to the many electron wave function from this perspective. So 65 is the invention of this theory and the approximation, which was good enough for solid state work, it turns out. All right, solid state physicists, they don't need great high precision. So physicists begin to use it, get great properties, great results for crystals to this day. Now the chemists had several objections. One is that the numerical results did not have chemical accuracy, which means they were not good to 1 kilocalorie per mole, which is what a typical chemist wants. So they didn't have to think about it. Plus, there were some quantum chemists, and their house organ is called the International Journal of Quantum Chemistry. This is an editorial statement that appeared in that journal. There's a misguided belief that the particle density can determine the exact ground state. It's not misguided. It's a theorem. And they finally came around. In 1990, what broke the dam with the chemists was that they threw out the local density approximation, introduced some empiricism, which chemists are wont to do, and found a better approximation for VXC that the physicists hadn't thought of and never would have because they weren't willing to do the empirical things that chemists were. That reduced the error by 90% for chemistry problems, and that is what made essentially chemists, many of them, turn overnight from configuration interaction to density functional theory. This was finally recognized in 1998 when Walter Kohn was awarded 1/2 of this Nobel Prize in chemistry because it's had such a tremendous impact on the chemists. Solid-state physicists have been using it for some time. So today, DFT is used universally by physicists, chemists, material scientists, everyone else interested in practical quantum mechanics, actually getting numbers. Now, I think this then, so I've told you a story of practicality, but this has implications for the people who worry about the meaning of quantum mechanics and the meaning of the wave function. I mean, here's a book, just a recent one, I'm sure many of you know these folks, and here many of the articles in this book have to do with the wave function and does it live in configuration space, does it live in real space, and what does it mean? But from a density functional perspective, none of this is relevant. All right? It's the density which matters, and we should be thinking about that. This is an observable in many ways. And so I don't exactly know where the entire density functional revolution, what impact, it's had no impact on the philosophers. They haven't got to it yet. But I think they should, because from a practical perspective, the actual calculators gave up the wave function a long time ago. And so I think for certain there'll be some interesting questions that will circle back to what Hans Primas said, that there's a revolution in the way one thinks about chemistry based upon this theorem of Hollenberg and Kohn, which, by the way, if you look at the most highly cited papers in all of the physics literature, the first 5 of them are all density functional papers. That's the entire physics literature. Thank you.
You made excellent time. So we have 20 minutes for discussion. So let me form a queue here. So you start, and then I'll get some. So Christian.
Yeah, thanks for this nice talk. You showed very briefly a quote by Hans Primas, who of course wrote extensively about this,
right.
But I didn't know the quote yet. So he says that it proves the feasibility of a complete renormalization of quantum chemistry.
Right.
Renormalization, does he mean that as a metaphor, or does he mean it like in a way that would remind us of like what happened in, for instance, QED?
Oh, no, he means, he's talking about the superfluous nature of the wave function. What's interesting is that Primas writes this paper very, very early. Later, he writes entire books about philosophy of chemistry and doesn't mention it at all. And I don't know what that means exactly, but he never comes back to it. It's a very long paper in '67, and then there's nothing.
Okay. So next person is Ariana.
Thanks. Okay, this will be a quite ignorant question, but you explained that these methods appear to work because there was a very good agreement with experiment.
Yes.
You said this 90%, I mean, so my question would be, what kind of observables were computed? Everything, or some things could not? For example, what about phase transitions and so on? I'm just wondering.
Yes. Well, the 90% had to do with chemists, and so what they mostly were interested in were things like the binding energy of molecules. All right, so if you can't get that right to 1 kilocalorie per mole, they weren't interested, and the local density approximation could not do that, but the simple improvements that were made, Axel Becker is the chemist who's most responsible for this. It gets that right. In chemistry, you need to know things like, well, for example, barriers to internal rotation have a lot to do with chemical reaction rates are based on barriers, Arrhenius rates, those sorts of things. In solid-state physics, people successfully calculate phase boundaries. They calculate cohesive energies. They calculate the spectra. Everything. Yes, it's remarkable. All the excited state properties too, because the green function, the propagator, is a functional of the density also. Now, who knows what that functional is? Nobody knows. But the fact that in principle it's true is what's sort of interesting.
Alexei.
I was puzzled by you saying that you couldn't find reference in methodological literature to the density function. Maybe I'm completely wrong here, but it was my feeling that the density operator, the density matrix, has been used in quantum theory since 1930.
Yes,
and
that's
it was
the-
a fairly well-known thing.
Yes,
But how
yes.
much it was spread, and maybe it's part of what Christian was telling us, how kind of certain methods get appropriated. So it could well be that quantum chemistry was sort of outside of that thing, but I would basically suggest kind of that may not be the origin of the thing, but I suspect that if you go in and check Landau-Lifshitz, a volume maybe on electrodynamics of continuous medium,
Yes.
you'll probably find it there. And then maybe with some further references of when
No. You're right. Density matrix methods have been around since Dirac invented them. And the chemists in particular had worked very hard on density matrix methods. And what they showed was that you only need the two-particle density matrix and you can get everything. The density is the diagonal part of the one-particle density matrix. And they refused to believe that that was all you needed. And they all said you need the two-particle density matrix. So this theorem shows that that is not the case. And there continues to be a large literature of density matrix things, but this is even less information in a way than the density matrix. In fact, there have been recent breakthroughs in doing it with the density matrix, but that's not the case. The closest one has, as I mentioned, is the Thomas Fermi method. And there were a great many elaborations of Thomas Fermi. And in fact, it's an interesting little piece of many-body theory that the many-body theorists jumped on corrections to Thomas Fermi theory, trying to make it better and better. But again, there was never in any of their minds the idea that this could ever be exact. It was just better approximations.
Okay. I think I missed like a hand like in this. Okay, show.
To clarify, when you said this function, the density function refers to all observables, I found it a little strange because before you show us this question of where the copper is in
Right.
the alloy.
Right.
So this function won't tell us where each atom is, and
Right.
of course, and we have ways to locate if we are looking for each atom.
Right. So this is a theorem of principle that says that all of these observables are in principle functionals of the density. And many chemists to this day say, but it's a long road to what I want to know. True. It's true. But from a thinking point of view, it's turned out to be very liberating for chemists to know that this theorem is in the background, that they don't have to deal with these billion-term determinants that somehow, beyond our comprehension for most difficult problems, that the density is enough. And what that's done is it's allowed chemists to make better and better guesses for this exchange correlation function. And they built empiricism into it, but it all, in the end, are just functionals of the density. In fact, they're often local functionals of the density. So in that sense, it's been liberating. But you're quite right. In order to actually calculate many things you need, rather than going through the green function, which is what you should do, they use the zombie wave functions to do the calculations, and they get remarkably good answers, and nobody understands that either. This field is fraught with problems of principle that the practitioners just don't care about because they want answers, right? And so there's a very small, dedicated group of people who are working on the foundations part of this, but it's very small because the answers are so good.
So in a sense, you're talking about a field where we have a few levels of understanding, and there are some connection between them, but usually you don't care too much about these connections.
Depends on who you are, but a typical chemist, in fact, it's gotten to the point where it's so easy to do these calculations now. For big molecules, hundreds and hundreds of atoms, you buy a code, and experimentalists buy the code, they do the measurement, and they run the code, and they don't care what's inside the code.
But this might perhaps also explain why some of the philosophers who are interested in the foundations are not so much interested in that.
Well, yes, but they should look at the practitioners and say, you should be interested. Isn't that what philosophers do? They say, you should be interested.
Yeah, but nobody listens to it.
I'm sorry.
So I think Ariana.
There is still a moment. I'd like to ask a follow-up question, because you said one can use this to compute phase transitions. So
Phase boundaries.
Phase boundaries, I mean, parameters of phase transition. So in the spirit of Christian's talk, I was wondering whether there is a knowledge transfer to high energy physics, where people are computing this.
Yes, the transition hasn't gotten quite to elementary particle physics. It has gone to nuclear physics, because everything in the theory applies to nuclear physics, and you will find there's a group of people who do density functional nuclear theory. The trouble they have is more, they're dealing with model potentials all the time, and they don't have the exact Hamiltonian. But apart from that, they're using the same methodology.
Is this plasma?
It's used for plasmas also. So is there a thermal generalization? You might ask, is there a time-dependent generalization? I talked about stationary things.
Plasma is also used in particle physics.
And yes, and the answer is yes. There's a time-dependent generalization also. Yeah, that's about 30 years old.
So Christian gets a follow-up.
Thanks for allowing a second question. Especially from the point of view of solid-state physics, I think most solid-state physicists would subscribe to the notion that there's two traditions that essentially have been competing over the second half of the 20th century. The first tradition being one of model building, and the second tradition being that of first principles calculations,
yes,
density functional theory, and so on. So for quite a while, the model builders had the upper hand. And since, I don't know, probably only the 1990s, it seems that the luck is in a way changing a bit, and that the density functional theory people are getting the upper hand. But at the same time, somehow this development comes full circle, because for the formulation of exchange correlation functionals, you now, more than earlier, use insights that come from many body theory, that come from the model-based tradition. Can you comment on that?
Yes. One of the reasons that the model builders and the many-body theorists actually disdained this entire business for quite a long time is that there is no systematic way, if you make an approximation to this exchange correlation function, starting with this local density approximation, there is no systematic perturbation theory, there's no systematic way, there's no small parameter to do systematic corrections. So it's uncontrolled. And people don't like uncontrolled approximations. And so in the physics community, people started using it in the 60s and didn't do anything until the 90s. They just kept using this same approximation because it was good enough for government work. But when the chemists finally made this big leap, it was such a big improvement, then the physicists have now adopted the chemical methods. The many-body people, by and large, would rather still not deal with it. They would rather go back to some of the very basic foundational work in many-body theory, the Dyson equation, and calculate the self-energy, and now people do that numerically. Computers are good enough to do it. And so it's only a tiny, tiny sliver of, so I would say the density functional people have not gotten the upper hand from a cachet point of view. Many-body theory and model solid-state physics remains the sexy thing to do. This is Pauli's Schmutzphysik, right? Calculating the numbers, and it's regarded as mechanics work by some people. But there's a tiny number of people, and you've been involved in some of this, trying to reconcile these two together, and that's where the progress will probably come. But the number of people in this many-body community that you told us about is enormous. The number of people in this density functional community is enormous, and the overlap of those is very tiny. And perhaps there'll be more of that, but it's not the case yet.
So before I close the session, I feel remiss as the chair, since you made these kind comments about what a wonderful community we are, to not point out that I recommend that you give the same talk, like in front of David Albert and Tim Maudlin, or in front of David Wallace in Oxford, and I think the reception will be very different. And on that note, let us thank the speaker.
Thank you.